So in this video, I'm going to be explaining nucleophilic addition. So the general mechanism for a nucleophilic addition is you're going to have an electrophile, which in this case I'm going to use cyclopropanone as the electrophile, and you're going to have a nucleophile, So this is not nitrogen, it's just N for nucleophile, which is either going to have a lone pair or it's going to have a negative charge. And what's going to happen is this nucleophile is going to donate an electron, so that's what the curly arrow indicates the movement of electrons. It's going to attack this partially positive carbon, and it's going to break the pi bond between the oxygen, and now it's going to form an intermediate that looks like this, where the nucleophile is added. And now in the case of a nucleophilic addition to carbonyl compounds, you're going to be using acid, so H3O plus, which now what's going to happen is this negative charge is going to attack one of the hydrogen atoms, and it's going to be added, converting it into an alcohol, which would be the final product. So OH, and then you're going to also have the nucleophile that's just been added. So that's the general mechanism for nucleophilic addition. So one of the first reagents you're going to see in your lectures would be a Grignard reagent. And what that is you're going to have some kind of alkyl chain, which I'm just denoting by R. Could be methyl, ethyl, propane, whatever it is, doesn't even matter. And it's going to be bound to Mg or magnesium, which is going to be bound to Br or any other halide. So, but it's most usually it's going to be bromine, but it could be any halide. So I'll denote that with X. So the most basic Grignard reagent would be a methyl Grignard. So that's going to be MgBr as the example. And what happens here is because magnesium has a +2 charge, bromine only has a -1, that's going to mean to balance this charge, this carbon must be holding a -1 charge, which is very unhappy. That's highly reactive. It's not how carbon obviously likes to be. And this is important because it means that this carbon can act as the nucleophile in the reaction. So Grignard reagents are used to add the nucleophile, which is usually an alkane or an alkyl chain, to a carbonyl compound. So I'll put an example here. So for example, if you've got propanone, you could use a Grignard reagent to add this methyl group onto the second carbon. And again, that's because this second carbon is going to be acting as the electrophile because it's got a partially positive charge, whereas the oxygen has a partially negative charge. And like I said before, this methyl group is, it's partially negative, not partially positive, due to the charges on the MgBr. The electron that's being donated to the electrophilic carbon is not actually coming from the carbon itself, it's coming from the bond between the carbon and the magnesium, but the electron that it's donating is much closer to the carbon than it is to the magnesium. So then what happens is this carbon with its negative charge is going to attack the electrophilic carbon here. That's going to break the pi bond between the electrophilic carbon and the oxygen, or in the carbonyl group, and that is going to lead to the formation of this intermediate, O- and CH3. So you've just now added this methyl group on to the propanone. And then this intermediate through is going to be neutralized because it's got usually an acid, or always actually, and that's going to end up forming this compound here. So now we've got a tertiary alcohol because we've added this methyl group and we've protonated here because we've broken the pi bond. So as I was kind of alluding to, this also works for aldehydes as well. It doesn't have to be a ketone. So let's just say we've got something like this. We could add the same Grignard reagent, and now we're going to have this positive carbon is going to be attacking this carbon here, the electrophilic carbon, and we're going to lead to the formation of this intermediate, which is eventually going to form this compound here, which again is, or which in the case of aldehydes will be a secondary alcohol rather than a tertiary alcohol in the case of ketones. And that's going to occur because this negative charge is going to result in the protonation of the intermediate. So here's an example using cyclopentanone and an ethyl Grignard. What do you think the product would be? So skip the intermediate, but the final product. So this here is going to be the final product. It's going to be cyclopentanol with, as a tertiary alcohol, where there's also going to be an ethyl branch that's just been added. So the last thing about Grignard reagents is whenever you're starting with a ketone, you're going to end up with a tertiary alcohol. Whenever you're starting with a aldehyde, you're going to end up with a secondary alcohol, except in the case of formaldehyde, which is, in case you didn't know, it's just the aldehyde from methyl group. So the reason that you're going to end up with a secondary alcohol, in case you hadn't already picked it up, is because this is the reaction which we've already covered. This is the general mechanism, and you're going to end up like this. So this is what's just been added using the Grignard reagent, and now you're going to have these two hydrogens still. They're going to remain, obviously, and that's going to be the alcohol. So because there's only one carbon, you're just going to end up with a primary alcohol every time. So the next reagent you're probably going to learn about would be lithium aluminium hydride, which is this compound here. So it's lithium with a positive charge, and then there's going to be aluminium hydride, which obviously aluminium has a +3, so all of these hydrogens, there's going to be 4 extra electrons, which gives it a negative charge. And now these are not directly bonded, but it's going to be an ionic or charge bond between the two. So lithium aluminium hydride is used as a reducing agent. It's a very strong reducing agent. And just to get this out of the way, it reacts really aggressively with water, and that's going to produce hydrogen gas, and which is obviously extremely dangerous. You don't really want to get it mixed with water unless it's part of the reaction, which in many cases it is, but you do that after it's reacted already with whatever you're trying to reduce in the first place. So lithium aluminium hydride is used to reduce a number of compounds, but particularly, and all you'll need to know at a first year level, is that it's used to reduce amides, esters, carboxylic acids, and nitrile compounds. So the reason that it is classified as nucleophilic addition still is because because there's 4 hydrogens, one of them is going to have a negative charge, and that is going to be your nucleophile. So hydrogen is the nucleophile when you're talking about reactions with AlH4. So I'll start with the reduction of amides to amines. So we've just got an amide here, and that's going to be reacting with lithium aluminium hydride. That's the H that's going to be donated, and then we've got a negative charge on the aluminium. So what's first going to happen is there's going to be a nucleophilic attack to the carbonyl carbon, which is going to break the pi bond firstly, and it's going to form this, which we're going to now have a negative charge on the oxygen, and that's going to end up being bound to the aluminium. And sorry, the negative charge is still on the aluminium. So from here, this lone pair of the nitrogen is very important, because that's going to form a pi bond with the carbon here, and that's going to break the sigma bond between carbon and oxygen, and that is going to eliminate the oxygen. So now we're going to end up with this compound. Oh, and sorry, there should be a hydrogen there, which that's my fault for not including it. But now we're going, so we're going to end up with this compound here. And because this nitrogen still has its hydrogen, it's now got 4 bonds, which we know is wrong for nitrogen, so that's going to be positively charged. And the final step of the reduction is a further reaction with lithium aluminium hydride, which ends up forming, which happens by another hydride. So you're going to get another hydrogen that's going to attack here at the same carbon, and now this is going to break the pi bond, balance the charge on the nitrogen, and you're going to end up, now you're just going to have the amine itself. And in this final step, that's when water would be added as well to destroy any of the leftover aluminium salts. So then now you're just going to have your amine, and you're not going to have to worry about any lithium aluminium hydride that's left over, because it will be destroyed by the water. Okay, so the next reduction we're going to be looking at is the reduction of esters with lithium aluminium hydride. So I've gone ahead and already set up the starting reagents, and the first thing that's going to happen again is going to be nucleophilic attack from the hydride to the carbonyl carbon again. Similarly, this is going to break the pi bond between the oxygen, and you're going to then be left with this intermediate, which now is going to donate to the aluminium, which is the same as we were looking at before, and then you're going to have, and that's going to be negatively charged again, with lithium here positively charged. Where it's different though is, instead of the pi bond between the oxygen and the carbon breaking, it's not going to break, it's going to reform, the sigma bond, it's going to reform the pi bond that it was just broken, and that's going to kick off this oxygen here. So now it's been reduced into the aldehyde, but it's going to further react with more lithium aluminium hydride, and that's going to occur by nucleophilic attack again from the hydride to the carbonyl carbon. I'm just going to break the pi bond again and form this same intermediate almost, except without the R group and the oxygen. It's pretty much the same thing. And then you're going to end up with, and that's then going to be through an acid workup. You're going to have, because this is an unstable bond since it's got a charge on the aluminium, so then you're going to have here, from that bond is going to be donated to a hydrogen from the hydronium. So, and you're going to end up with the alcohol and that's for this side, for the carbonyl side, and for the I don't even know what to call the ester side. I guess it's more like an ether, but whatever. You're going to have a similar, pretty much the same as what goes on here, and it's just going to reduce it into an alcohol. So that would just be the R to the OH. That would be the way that you would denote the second product. So these are the two products. So the third and second last that we're going to cover for the reduction using lithium aluminium hydride is for carboxylic acids. So we can have carboxylic acid like this, and we'll have our lithium aluminium hydride. The first step is deprotonation of the alcohol or the hydroxyl. So what happens is this, from the bond between the aluminium and the hydrogen and the hydride, that is going to be donated to this hydrogen here, and you're going to be left with this. And then the electron held between the bond between the oxygen and the hydrogen is going to go to the oxygen. So now you're going to have this compound here as an intermediate, and your leaving group, and I haven't been necessarily illustrating it, but this is quite important. The leaving group in this case is going to be hydrogen gas, and you're also going to have AlH3, which we've had in most of them, but hydrogen gas is very important here. So now there's going to be a lithium from this reaction that is free now, and it's going to be stabilizing. The negative charge on the oxygen for long enough so that it can react again with lithium aluminium hydride. So we've got another lithium aluminium hydride, and so now this time the hydride is going to attack at the carbonyl carbon. It's going to break the pi bond here, and you're going to be left with a compound that looks something like this. And that's going to be stabilized by another positively charged lithium, and here it's going to be bound to the AlH3. And the negative charge will not be here, it will be on the aluminium. So then there's also going to be still this lithium that's going to be stabilizing the charge. But the next step occurs by formation of a double bond here and the breaking of this bond there. So now you're going to be left over with an aldehyde. That's going to look something like that. And of course you still have the hydrogen and the second product, which in case you're wondering what happens to this oxygen, it's going to form lithium oxygen AlH3. So this is the main product, and this is just a byproduct. So when you eventually do the aqueous workup to destroy any of the lithium aluminium hydride left over, and any of the lithium salts, you'll end up with an alcohol because it's going to protonate the aldehyde as well. So the last reaction with lithium aluminium hydride we're going to be looking at is for nitrile. So if you've got a nitrile compound like so, this lone pair of electrons is going to attract the lithium portion. So we'll use dotted lines to show that. It's going to attract it at first, and then you've got the AlH4 obviously, and that's going to have the negative charge again obviously. So because it's already kind of forming somewhat of a bond, not really, it's just attracted to the lone pair. Once the nucleophilic attack occurs onto the carbon here, you're going to get the breaking, because there's 4 bonds, you're going to get one of these triple bonds is going to break, so one of the pi bonds, and it's going to donate the electrons to the lithium And what you're going to be left with is this. So this is the hydrogen that was added from the aluminium hydride. And you're going to have a double bond to nitrogen, and it's going to be a single bond to lithium. So now the AlH3, which we'll draw here, it's going to get close to the lone pair on the nitrogen as well. But in order for anything to happen, this bond first will break, the pi bond between nitrogen and carbon, and the electrons are going to be donated to aluminium, which is going to break one of these bonds, the electrons will then move to the carbon here, and you're going to be left with this weird looking compound. So from here, the next two steps are hydrolysis of this imine salt. So you'll have the compound and you'll add water. So you can just draw it like that because this is the only bond that matters. And what's going to happen is this bond between lithium and nitrogen is going to break, and it's going to go to the hydrogen. Now this bond is going to break, and you're going to be left with a negatively charged OH ion, which, since this is going to be a leaving group, it's going to be kicked off from this imine salt. There's going to be a positively charged lithium, which can be balanced by the negatively charged hydroxide. You're going to end up with a compound like this. And again, it's going to react with water in a similar way, but for the aluminium group this time. So you're going to have this bond between the nitrogen and aluminium is going to break. It's going to pull in this hydrogen off water. This bond breaks. You've got a negatively charged hydroxyl, positively charged AlH2. They will balance out, and you'll end up with this primary amine. And the hydrogens I've drawn in have been added, which we've already discussed. So that's why I'm drawing them in. So that's it for this part, and the next part will be, we'll start with some questions on nucleophilic addition using lithium aluminium hydride, and then we'll move on to the rest of nucleophilic addition.